Hello, everyone, and thank you for joining us. My name is Amanda Kramer, and I am the Alumni Engagement Program Manager at the University of Colorado Boulder's Lead School of Business. Welcome back to our fifth COVID-19 webinar series. These are certainly trying times, and here at CU Boulder, we have gathered our world-renowned faculty to provide frank and timely insights for life during the COVID-19 pandemic. Today is the second of 4 webinars in this COVID-19 related webinar series. To view upcoming webinars, please visit our website at colorado.edu/business/alumni. Click the drop-down arrow and click Attend Online Webinars. For today's webinar, we're so excited to welcome Assistant Professor in the Department of Computer Science and the BioFrontiers Institute, Dr. Daniel Larremore, here presenting COVID-19 surveillance testing, a way out? A few housekeeping items before we begin. First, if you have any questions now or during the presentation that you would like to ask Dan, please send a question through the Q&A interface. We will monitor questions as they are submitted, and Dan will respond to them at the end of the presentation. As a reminder, for optimum audio quality, we do have everyone on mute except for myself and our speaker. If you experience any technical difficulties during the webinar, please notify us through the chat interface, and one of our support specialists will touch base. Lastly, a link to access the webinar recording will be sent to all registrants tomorrow, along with a survey link and supplemental resources from today's presentation. Now, I am excited to introduce today's speaker. Dan Larremore is an assistant professor in the Department of Computer Science and the BioFrontiers Institute at the University of Colorado Boulder. He is also an affiliate of the Department of Applied Mathematics at the University of Colorado Boulder and is a member of the external faculty of the Center for Communicable Disease Dynamics at the Harvard T.H. Chan School of Public Health. His research develops mathematical methods using novel combinations of networks, dynamical systems, and statistical inference to solve problems in 2 main areas. 1, infectious disease epidemiology, and 2, computational social science. This work focuses on generative models for networks, the ongoing evolution and genomic epidemiology of the malaria parasite, and the origins of social inequalities in academic hiring and careers. Dan obtained his PhD in applied mathematics from the University of Colorado Boulder in 2012 and holds an undergraduate degree in chemical engineering from Washington University in St. Louis. Welcome, Dan, and thank you so much for being here. I'm going to hand the webinar over to you now.
Well, thanks so much for having me, Amanda, and for everyone for tuning in. I know that testing is something that has been in the news basically nonstop since the pandemic started, both here in the US and around the world. And so I'm excited today to tell you a bit about the research that we've been working on and some ideas that we have about how COVID-19 surveillance testing could help us find a way out of this pandemic, potentially sooner than the vaccine that is supposedly going to become available sometime in the next year and will arrive. So with that, let's get started and just talk about a little bit of background on testing in general. There are 2 kinds of tests that we typically talk about for SARS-CoV-2. One is a virus test, and the goal of a virus test or a virological test is to ask, where is the virus right now? Who currently has a virus in their system and who's infected? And we can get this through a variety of means. One is what you have maybe heard of, the nasopharyngeal swab or the NP swab or the brain tickling swab. This is the really long Q-tip looking thing that goes way back into the nasopharynx and tries to get a sample there. You can also get a sample collected by an anterior nasal swab or an AN swab, and this is more up in the nose picking region. And of course, we also know that we can get concentrations of virus in the saliva and identify people who are positive from samples in the saliva. So all 3 of these different sampling sites allow us to figure out where's the virus now. And we know that after exposure, people are typically positive here for 1 to 3 weeks. And this is really critical for isolation and contact tracing. And that's what we typically mean by testing. I won't talk about this so much today, but there's also serological testing that's looking for antibodies. We know that antibodies show up later on. Those signals don't really get picked up in your blood until at least a week later. But this is more about asking questions of the form, where has the virus been? Not where is it now? You're often positive by antibody tests for months or even years. And this is really a retrospective tool. It's key to understanding what happened in the past and to understand population transmission rates. So what we're going to focus on today is really virological testing. Where is the virus right now? So the overall picture of what we'll talk about today is how we need to rethink the way that we talk about sensitivity for virological testing. And to introduce this topic, I want to build a little bit of intuition with a little diagram of the viral load. So this is kind of the perspective of what is the virus population looking like in your body as you are going from exposure to infected and eventually to recovery. So it starts out after exposure with colonization. This is when the virus is replicating in your body, but it's at such low levels that we basically can't detect it. It's sometimes called the eclipse phase. After that, the virus really gains a foothold and enters this phase of exponential growth and picks up here. We achieve what's called a peak viral load at some point in the next few days. And during this phase, within the next couple of days, usually symptoms develop. It's also during this phase, which is shaded in gray here, where people are capable of exporting the virus to others. In fact, it's been found in study after study across everything that's known so far, that there have been no cases of transmission more than 10 days after symptom onset. And so this window of exporting the virus is actually not that long. Of course, then the viral load slowly gets pushed down by the immune system in an ideal scenario, and you get clearance. So the question is, how can this kind of picture help us rethink testing? And what use is this diagram even as a cartoon? What we're going to do is imagine how testing interacts with this diagram. When we describe something called the analytical sensitivity of a test, what we mean is the ability of that test to detect something in the sample. And it's usually expressed in units of minimum detectable concentration, or a limit of detection. So a highly sensitive test can detect lower concentrations of molecules in a sample. And so it has a high analytical sensitivity and a lowered limit of detection. On the other hand, a low analytical sensitivity test is going to cut across this curve at a higher point, meaning it requires a higher concentration of the virus to actually show that there's a positive. So the gold standard for testing is called PCR, and it's a high analytical sensitivity test. It stands for polymerase chain reaction, and it takes concentrations of DNA or RNA and repeatedly doubles that concentration up until it's detectable using a machine. Okay, so importantly, we're going to use the fact that these two different tests cut across the viral load trajectory at different points to make the following argument. There's not that much of a window when you're pre-infectious and positive by a PCR test, likely on the order of hours, maybe half a day. And during that time, the viral load is really rocketing upward. Then there's this period in the middle where somebody would be infectious and positive by either a low sensitivity test or a high sensitivity test. And then this period off to the right where you're no longer infectious, but you still may be positive by PCR. And in some cases, this is extended weeks or even longer than a month, where people have small amounts of viral RNA still floating around their system, but there's no virus that can be infectious. So now we want to imagine a scenario where the person in this viral load trajectory is going through some kind of regular testing regimen. So if you had a low analytical sensitivity test that you were taking, let's say every 3 days or maybe every 6 days, 7 days, that's likely going to give you a positive sooner than if you used a high analytical sensitivity test, but you were more sporadically tested. So just from the picture alone, we're going to start to build this intuition that it doesn't matter so much what the sensitivity of the test is. What matters more is the frequency with which you do the testing. So this is the picture. And it's worth distinguishing different kinds of testing before we move on. So medical doctors really care about this analytical sensitivity. The goal of a test that's called a diagnostic test is to detect molecules in a sample for diagnosis. So you experience some symptoms and you go into your doctor and you say, like, why do I have this cough, and why did I have this fever last week? What you and your doctor really care about is figuring out why you are sick or why you were sick, so that you can understand your symptoms then and maybe some symptoms that linger into the future. So there's less of a timeliness element when we're thinking about diagnostic tests, because that's information that you and your doctor can use basically at any point. But from the public health point of view, from epidemiology, the key is to detect infectiousness as early as possible so that we can break transmission chains and give this person information that they need to go into isolation, protect their family, and protect others around them. So the needs of these different kinds of tests differ. The high analytical sensitivity test is going to be great for the doctor, but some tests that detects as early as possible is going to be better from the point of view of public health and really mitigating this ongoing pandemic. So in the modeling study that I'll tell you about today, we first combined what's known about viral load trajectories. From all the different studies of people throughout the course of infections with this disease, what do we know about the actual shape of the curve going up and down? Then we considered how the assay's limit of detection, assay here just means that test, PCR or some alternative, how that interacts with those trajectories. And then we considered how the viral load could relate to infectiousness, the ability to actually spread the virus to others. So we asked, what would be the impact of a surveillance testing regime with particular limit of detection, a particular testing frequency, and then a given sample to answer turnaround time, the amount of time it takes from either the swab or the saliva to actually getting a diagnosis back to you from your doctor or a text to your phone or something like that. So that's the setup. So here's the model for viral load. It's really simple. It starts at day 0, that's the day that you were exposed, and goes out for 21 or so days. And the idea is that we're going to just parameterize this model with exponential growth, which looks like a line when we have a log scale here. So this is measured in copies of viral RNA per milliliter of sample. So we have exponential growth followed by exponential decay. And the model is random, it's stochastic, where we have these 3 control points, one for the delay until this exponential growth regime starts, another for the height of the viral load and the timing of the peak viral load, and then a variable decay, so some point out here that governs how long it takes for this virus to decay. So that's the basic idea. What we can then do is ask how a test would interact with that. So here I'm showing 2 tests, one in the pink. This is your gold standard PCR test. It's got a limit of detection of around 10 to the 3 copies per mil. And then this is another test at a limit of detection around 10 to the 5th copies per mil. This is around what you might expect from an RT lamp-based assay, which is an isothermal assay, the kinds of which have been developed at CU, University of Wisconsin, and other places. But critically, if we imagine an asymptomatic person who doesn't know that they're infected, and they come in, they happen to get tested on day 6, this point right here is above either of these 2 lines. And therefore, this person is going to get a positive diagnosis regardless of which test they use. By the way, you may have heard of something called the CT count or the cycle threshold count that applies to PCR. The cycle threshold count is basically the number of concentration doubling cycles in the PCR process that it takes for a sample to get amplified up and then finally be positive. So if you start at a higher baseline concentration, it takes fewer cycles. And so the CT count is lower for a higher concentration. So that's why down here at the limit of detection for PCR, the CT count is written as about 40, whereas here it's about 33. And as we move higher and higher, you get to CT counts of even up into the teens, or I should say down into the teens. Okay. So now we can think about how this kind of testing would interact with infectiousness. So let's imagine that same person here who was infected on day 0, and they didn't know that they were infected until they got the diagnosis on day 6. So if that person got information on day 6, that allows them to isolate and remove from the population 65% of their infectiousness. So the blue, they were still infectiousness, but the black they were able to avoid because they had that information. So in this model here, for those interested in the math, what we're assuming is that the infectiousness is proportional to the log of the viral load. This is consistent with some estimates from Hay et al. In Nature Medicine. But in the supplement of the modeling paper that we worked on, we considered some other extremes. In one case where it gets much peakier around the peak viral load, and then another case where it's just flat across the board while you're infected. And in either case, Some of our conclusions just moved a little bit, but the overall conclusions that I'll tell you about today were the same. So if this is what one individual looks like, but we know that that viral load trajectory that we're modeling is random and might vary from one person to another, we can ask what happens if we apply a testing regimen to a whole group of people. So that's what I'm showing you here. Across a horizontal axis, you can see what people's infectiousness values over the course of their infection were like for no test, daily testing, testing every 3 days, weekly, or every 14 days. In the pink, these are dots where you were diagnosed via a test with limit of detection 10 to the 3. So that's the gold standard of testing. And then in the gray dots, this is with a limit of detection of 10 to the 5th. So that's something more like a rapid LAMP test. And the whole point here is that there's not a huge difference between the pink and the gray in any one of these scenarios, except there is a pretty big difference between daily, 3-day, weekly, or 14-day testing. So the blue bars here are medians, and anytime the dots are colored blue, that's somebody who actually made it all the way through the testing regimen and was infectious and then no longer infectious, and the test failed to catch them at all. So you can see that if we're testing people every 14 days, there's a fair number of people in this distribution who basically went through their entire infection, but were never identified. So this is what things look like when we look at individuals, but what we really care about is how these individuals are going to, as a population, spread the infection to others. So what we're going to do is kind of add up all of the infectiousness, including the people who had huge viral loads and the people who had relatively lower viral loads, including in our different scenarios, and bundle them up and ask about the amount of infectiousness in the population that remains after you institute a testing regimen. So here's what that looks like. First of all, let's look at the no test scenario. We assume that 35% of people are going to be behaviorally symptomatic so that they would self-isolate at symptom onset. Some of the estimates from Lombardy, Italy suggested that around 75% of people were behaviorally asymptomatic in the under 60-year-old population. But we think that the definitions here of symptoms, asymptomatic, pre-symptomatic, are a little bit slippery. So we increase that number. We just assume that 35% of people are going to understand that they may take precautions. If we test people daily, the testing basically causes everybody to isolate based on their positive test result. And just a sliver of people make their way onward to develop symptoms and isolate because of that instead of the daily testing. As we decrease the frequency of testing out to weekly and even 14 days, the fraction of people who are isolating based on symptoms increases and gets closer to the no test scenario. And the fraction of people who we catch through testing decreases and decreases and decreases. But again, the key point here is that the height of these bars isn't particularly different from the pink to the gray. In other words, it's not so much the sensitivity of the test that matters, it's more the frequency with which that test is given to people. So rather than present things as bars, what we know is that this virus spreads from one person to another to another. And so what we next wanted to do was ask, in a simulation model, what happens if we plug this kind of testing in these viral loads into a simulation model where individuals get infected, and then they go out and can infect others, but they're also subjected to some amount of testing. And so maybe they get caught before they spread to others, maybe they don't. What happens then? So what we can do is just plug these viral load trajectories into an SIR model. And an SIR model stands for susceptible, infected, and recovered. This is a standard, what's called compartmental model of disease spread. People are in one of those categories or another. You may have heard of these kinds of models as SEIR models, where there's another compartment before the I, in between S and I, which is for exposed. In this case, we actually don't need that compartment because we're modeling those individual viral load trajectories, so that's already incorporated into the infection. That exposed period is built in. So here's a model of 20,000 people with a constant low importation rate from the community. So individuals are constantly getting infected from the outside. And we have no surveillance testing at all. So this is just sort of a toy model. Maybe it's like a college campus, maybe something like CU Boulder. There are no specifics in this case, but it's a very simple model. It's called a well-mixed model where every individual in the simulation comes into contact with everybody else. So what you can see here is that we get the typical epidemic curve, right? This blue curve picks up and we get a peak of over 6,000 people infected at once. And then this decays as basically the entire epidemic burns itself out. And during this period, some people self-isolate based on symptoms, but because there's no testing, you don't even see the black curve here. So there are no people isolating based on testing. So now we can ask, okay, what happens if we institute testing in this model? So here's what things look like if you test weekly with a test with a limit of detection of 10 to the 3. That's like asking everybody in this population of 20,000 to do weekly testing. And so what you can see here is now the infection curve in blue is going up, but at the same time, we're catching lots of cases. So this black curve is bouncing around, and the self-isolation based on symptoms is bouncing around below the black curve because we're catching a lot of people via testing instead of waiting for them to just isolate based on symptoms. So in a sense, this is ideal, right? The number of people who are even going on to develop symptoms that causes their self-isolation is low relative to the number of people that we're catching in this COVID screen ahead of time. One quick point here is that you'll notice that the y-axis is also a lot lower. Now we're down to peak infections of around 300 people as opposed to peak infections in the previous case of 6,000. We can adjust this even more. This is with a limit of detection of 10 to the 5th, so something like a rapid RT LAMP test, where you're testing every 3 days. And now this axis is dropped even further. You're basically constantly battling the low-level importation from the community, constantly battling these small little micro chains of infection, but we don't see any big epidemic curve. And so the testing is basically counterbalancing that constant importation from the community in this case. So what this allows us to do is then summarize lots of those kinds of simulations where we ask, what are the total number of infections like when we have no test? So that's 100% of the total infections versus daily testing, testing every 3 days, weekly, or every 14 days. What you can see here is that testing weekly really limits the total number of infections that you have, typically down around 50% or below, but testing more frequently than every week, you really suppress and mitigate that epidemic. On the other hand, testing every 14 days really doesn't do much. You're spending a lot of money for that testing, but it's not really impacting the spread of the disease. And we saw that on the previous plot where a lot of those infections kind of made their way through pretty easily. We had a lot of blue dots on one of those earlier plots. So what I'm showing you above is this fully mixed model of 20,000 individuals, constant and low importation. But also in the paper, we used an agent-based model that's based on the micro-population structure of New York City to try and understand whether or not that affected things. And the gist is the plots look basically the same. Testing has a huge impact if we do it daily or every 3 days, and a pretty good impact if we do it weekly. But really beyond weekly, it's really not worth the surveillance testing. So the conclusions from this work were that test frequency really matters for screening and surveillance. But we can also ask about delays between getting the test done and the results. So back to our previous model, here's our viral load trajectory again. And let's imagine that the person gives the sample here on day 6, but they have to wait 2 days and they get the diagnosis on day 8. So what happens to this asymptomatic or pre-symptomatic person? Well, here's back to our infectiousness plot, where again, they're infectious and out in the community, and they don't know it in these blue bars. In the green bars, this person has been tested, but they're awaiting the diagnosis. And the black bars, they've finally gotten that diagnosis are isolating. So in this case, that delay caused us to drop from a 65% total infectiousness isolated down to just 31%. So now we can go back through our previous simulations and ask, what's the impact of delays in those other scenarios? So here again, we have no test, daily testing, testing every 3 days, weekly, or 14 days. What I'm showing you in the small numbers here are the days by which we delay the results in the model. So a 0-day delay, that's like a point of care test, 15, 30 minutes, maybe up to an hour. This is a 1-day delay and a 2-day delay. And critically, what you can see is that even adding a single day of delay really starts to have a big impact on people's infectiousness distributions. In fact, you can see that if you're doing weekly testing, but you're delaying the results by a day, these median values of infectiousness really, really creep up. Okay, so we can do the same thing as before and kind of bundle this up over a whole population and now ask what's the difference across the whole population for the amount of infectiousness that we can remove. And you can see that as we increase the delays, it really has a dramatic impact on our ability to remove infectiousness from the population by giving people information and allowing them to isolate. And the arrows in this plot are really important because I want you to compare what's the difference between a test with a limit of detection of 3, that's the pink bar here, but with a 1-day delay, versus a point of care test with limit of detection 5. And this comparison here suggests that actually, if you could use the less sensitive test, but get the results back sooner, that would be better than the gold standard test, but with the results delayed by a day. So in any of these scenarios, you can compare the PCR with a 1-day delay versus something like an RT lamp test with a 0-day delay. The 0-day delay with the RT lamp test would be preferred. I also want to point out that we assume 0 contact tracing efforts in this model. We just assume that the only way that you know that you're infected or you go in for a test is just by the surveillance testing. But of course, if you also had contact tracing, all of the amount of infectiousness that you could remove should be increased. So again, we can plug these into the simulations for the SIR models, and both with the 20K people and the model of New York City, we see basically the same results, which is that an otherwise great testing regimen can really be ruined by substantial delays. Okay, so our goal here was to really understand which factors matter, limit of detection, test frequency, and results turnaround time. And really what we've concluded here is that the assay's limit of detection within some reasonable range really doesn't matter as much as we thought. It's the test frequency and results turnaround time that are critical for the kind of testing that has an impact on public health. And again, to reiterate, this is a different kind of testing that we might need for the diagnosis that your doctor gives you. For that, you of course will want the best clinical diagnostic test possible. But for public health, the needs are actually really different. So what about delays across the US? Okay, so I like Twitter, and I got curious about this in July and asked, what's the current national picture for COVID test turnaround delays, and asked people for results. Okay, that it turns out is not a good idea because then people just respond in the Twitter thread. So I teamed up with Brendan Klein. He's a PhD student at Northeastern University who scraped this big Twitter thread, parsed all the results, and then we also launched a survey together and got around 1,000 responses. This is by no means a systematic sample, but what you can see over here in the plot on the right is the test turnaround in days, going from 0-day delay up to 21 days of delay where people were waiting for their results. Again, this was back in July, but just to give you some idea, the circle in each line represents the average of the respondents, and the boxes tell us where 90% of the people responded. So this is the 5th percentile and the 95th percentile. Okay, so the total number of respondents was 885, and you can see state by state the number of respondents. When there was only one respondent, I kind of tried to gray it out a little bit. And no statistician is going to look at this and say that this is good statistics. The point here is not to make a good statistical point, but instead to just look at these reported delays. Because remember, in the previous modeling, we had argued that even a 2-day delay could really diminish the impact and the value really in terms of information of test results. So that line is right here, shaded very slightly in red. And the key point is just that the vast majority of these states, these people who reported on average, were far above this line. There was no state that was really exceptionally good. In our state of New Mexico here, we only had 4 responses, so I'm not really willing to lean on that. There's a high variability across states, some people with very rapid results, some people with very long delays, and no state was really consistently good. Okay, so not great statistics, but it does paint a pretty grim picture. And that was back in July. So we can also ask about what about mitigating an ongoing outbreak? So what we decided to do was we simulated outbreaks where there was no testing until prevalence reached 4%. So this is the number of weeks after surveillance begins, and the 0 point here lines up with the 4% mark, and this is the prevalence of the disease in the population. So it grows and grows and grows, and then at this point, we turn on the testing. And we used a test with limit of detection 10 to the 5th, thinking that the previous modeling had really suggested that that limit of detection shouldn't really matter too much. And so we'll use the cheaper and more rapid test. So what you can see is the epidemic curve if there's no intervention. And then you can see the different epidemic curves if there is intervention, if we do turn on the testing. And this is the best one here. This is 75% participation, testing every 3 days. And what this did was it dropped the total number of infections from 100% down to 12%. On the other hand, if we did 50% participation, testing every 3 days, we'd drop it by 73%, down to 27. And so things look worse, as we decrease the participation rates and decrease the frequency. But even weekly testing with 50% participation drops the total number of cases by 42%. And this is not assuming anything about contact tracing or masks or any of those additional things that we know can push things downward. So aggressive testing with 75% participation really suppresses this epidemic on a time scale of under a month. So let's talk a little bit about the real world, because this is important. Our work has key limitations, right? This is a mathematical model. We know that in the real world, not everyone is going to want to get tested, particularly if positive tests bring bad consequences. So incentives matter. For instance, if your workplace is instituting regular testing, but upon getting a positive result, you're sent home without pay for 2 weeks, that means you're not going to want to get tested. Another issue is that positive tests might not actually cause people to isolate. It could be driven by irresponsibility, right? There's been a lot of talk of college students and the college students just want to party. We know of cases where people have gotten positive results and then gone to parties anyway, or had people over to their own house parties. Another reason that people might not isolate is due to misinformation. They might be led to believe that the test can't be relied on, or that the technology just isn't there, or for whatever other reason, mistrust the test. Another reason to think about positive tests not causing people to isolate is an economic need, right? If I'm providing for my family and I can't afford to take 2 weeks off of work to isolate, I need to keep going to work to provide for them. And that's a terrible bind for somebody to be in. So in the real world, the positive test might not have the impact that we would want. One interesting issue is that if failure to test or isolate, either to participate or to isolate once you get a positive test, is what we call homophilic, meaning birds of a feather flock together. Others in your community have the same, let's say, mask wearing, test adherence, isolation as you do, then the impacts are going to be heterogeneous, right? Some parts of a community are going to experience outbreaks because they don't believe in testing, or they don't isolate, or they don't wear masks. You'll get outbreaks there, whereas other parts of a community will not, because they, let's say, are adhering to testing. So just as some concluding thoughts here, the big conclusion here is that the test sensitivity is really secondary to the frequency and turnaround time for COVID-19 surveillance. It's important to understand that the sensitivity to detect molecules in a sample, that's that analytical sensitivity or limit of detection, is different from the sensitivity to detect infectious viral load in a person. And really, if we're looking about public health, this is what we should be thinking about, the infectious viral load in a person. We've also shown in this model that during an unfolding pandemic, the within-host dynamics of the disease really matter. It matters whether or not you develop symptoms after you transmit versus before you transmit. And in fact, one of the big differences between SARS-1 and SARS-2 was that with SARS-1, people often developed symptoms before they were able to transmit, meaning they could be isolated before transmission. With SARS-2, we know that this big issue is that people often transmit without any symptoms at all, whether or not they go on to develop symptoms. And so really understanding those within host dynamics matter. The bigger picture is that testing can help us create a COVID filter. And like the layers of a filter, that repeated testing with fast turnaround times can get people the information they need in time to isolate. So the overall conclusion here is that we really need to expand the use of rapid, convenient, and ideally cheap COVID testing. So this has been COVID-19 surveillance testing, a way out. I want to recognize some critical co-authors here. Roy Parker, who's the director of the BioFrontiers Institute at the University of Colorado Boulder, was instrumental in getting this work going, as was Michael Mina, a professor at Harvard School of Public Health, who's really been driving this forward and in particular advocating for rapid testing. Sam Zhang has also worked with me on developing some calculators where you can explore some of this some of these calculations on your own. That's on my webpage at larremorelab.github.io. And in these crazy times, I like to put stars by any of my collaborators who've been working with kids at home. And Roy gets a silver star. His kids are older. If they were small and he had a lot more to deal with, he'd get a gold star. But anyway, fantastic to work with these folks. There's more information on my website if you're interested, and I'm happy to answer any questions that you have. Thanks.
Great, thank you, Dan. We will move into the Q&A period. If you have a question for Dan, please submit it through the Q&A interface there on your screen. We already have some questions flooding in. We'll start with a question here from Joy. She says, can you explain more about the types of models that you use? What level of math is involved in understanding the epidemiology of a disease like COVID-19?
Oh, that's such a good question. So one type of math that we use quite a bit is probability, right? We know that the spread of the disease is not random, but it's probabilistic, right? If you're within 6 feet of somebody for, let's say, 30 minutes and they're positive and you're negative for COVID, you won't always get infected. You'll sometimes get infected. So the transmission there is what we call stochastic, and so probability is really critical. And in fact, you'll remember that in that viral load trajectory, the height by which you move up and the rate at which somebody falls down in their viral load, all that was also stochastic. So there's a lot of randomness involved in the modeling. From the point of view of the transmission of disease, of course, the basic models that we use there are what are called SIR or FEIR, compartmental models. And those are typical differential equations models. So we lean a lot on calculus there. So I'd say to really do a lot of this modeling, probability and calculus are really the key components.
Okay, great. Absolutely, that makes sense. Next, we have a two-part question here from Matthew. One part, I keep hearing about the possibility for rapid testing to become available over the counter nationally. Have you heard anything about this? And then the second piece would be, is there a preferred rapid test methodology, nasal or saliva?
I want to answer the second question first. I think that the methodology for rapid testing here, gosh, in my opinion, what's most critical is that it's convenient for people. For instance, what we've got going here on CU's campus are, sort of like picnic gazebo type tents. And you walk or bike up to the tent, take your mask off, spit in a tube, hand it to someone, they scan the barcode, you swipe your Buff1 card. It's like 2 minutes, 3 minutes, in and out. That kind of convenience really opens the door to testing in a way that's not quite available if you need somebody to help you, administer the NP swab deep into your nose. And so I think that if the goal is public health and widespread surveillance, then it'd be much better to do things based on saliva. In terms of, I think I forgot the first part of the question because I'm a professor.
Sure.
And I talk too much.
I keep hearing about the possibility for rapid testing to become available over the counter nationally. What have you heard about this?
Oh, right. Okay, that's another good question. So when it comes to rapid testing, FDA is very interested in making sure that the tests are safe and that they're used appropriately. So there are now some over-the-counter tests that you can use off-label with a physician to tell you that you should use them. And these are our point-of-care tests. They're rapid tests, often based on antigens. So looking for proteins in your saliva, quick turnaround, lower analytical sensitivity. But what FDA is not quite convinced of yet is that these kinds of things are going to be useful for at-home use. As one of the representatives, I think maybe the CEO of Abbott, a testing company, said recently, for us to be able to put these out there for like at-home use, we need to consider all these possibilities, like what happens when your test gets left in your hot car during the day? Is it still going to work? And so they have to test this much wider range of reliability until they get to that level. So, my hope is that FDA continues to allow for this innovation, but they have been slow to move on that. I think because when it came to COVID antibody tests, the other kind of testing that we talked about earlier, they really opened the floodgates there and got a lot of applications, which turned out to not quite be up to snuff.
Okay, thank you for that. We have a question stemming from this. Both Matthew and Bill have asked, they've heard about this Abbott ID Now rapid test.
Mhm.
Do you think that that will be capable of the accuracy and speed you need to affect the trajectory of the pandemic?
Yes. I mean, the truth of it is that if everybody in this country could get one of those Abbott ID Now tests, and everybody who was positive, the small fraction of people who are false positives and all of the true positives could isolate today, like, I mean, the pandemic would be over. We would really break the backbone of transmission in a hurry. So getting rapid tests out to people, really, regardless of the test sensitivity, as long as it's reasonable, all of these tests would serve the function of providing these sort of contagiousness or infectiousness indicator tests that are not clinical diagnostics, but serve the public health need.
Okay, great. Thank you for that. We have a question from an anonymous attendee asking, do you use any predictive modeling to predict the likelihood of a second wave of this virus that may have mutated?
Oh, that may have mutated? No. We're not doing any kind of larger scale dynamical modeling of like the trends in the population or anything like that. The modeling that we were doing here was really focused on the dynamics within a person during infection, and then how that would affect the kinds of models that people use for the larger scale forecasting. But we haven't plugged into any of those additional models. Importantly, if the virus mutates, it's likely that the tests that we currently have are going to nevertheless pick it up. So I don't think that the mutation in the virus would be affected or would affect the kinds of testing that we've talked about today.
Great. You proactively answered the question that came in immediately off of that. So that is great.
Okay.
Next is a question from Scott. He said, what is your opinion of pooled sampling? And if your opinion's favorable, how can its use be increased?
Right. So pooled sampling is a really cool idea. The idea is that, if we all spit into a tube, but then we combine that sample together, then if you test that sample and it's negative, then we all get a negative result. And so you've used up only one test to rule out cases in those, let's say, 8 people who are part of the pool. So that's great. What that allows you to do is it allows you to increase the frequency of testing, because now you have used fewer resources on any individual test. Of course, if the pool is positive, then each individual needs to go back and be tested. So fine. Pooling is this really clever idea to increase the frequency of testing. So to the extent that pooling increases frequency, it's great. However, doing pooling, doing it well, requires some amount of logistical sophistication, right? Like, you can't just do pooling, kind of in a slapdash way. And that logistical complexity really adds up to the point that if that additional logistical complexity gets in the way of more frequent testing, or it causes the turnaround time before the positive results get back to people to be increased, then there are really some trade-offs that have to be considered. So pooling, great for increased frequency, but may have some impacts on turnaround time.
Okay, great. Thank you for that. Next, we have a question from Jeff. He said, do you know if other countries have successfully used population test strategies as you outlined, what those results were, and what would happen if the US introduced such a strategy?
Really, the test beds for this right now are America's universities, right? They're trying to reopen, and research ours and from others have suggested that regular testing of everyone on campus is a way to really break enough transmission chains to safely reopen. So University of Illinois, Urbana-Champaign is maybe the university with the most frequent testing. They're testing everybody twice a week. CU Boulder, testing everybody on campus once a week. And other Colorado universities are also doing regular testing. Unfortunately, what's become clear is that it's not just testing alone. I mentioned over here about the real world that incentives matter, so that people won't want to get tested if they feel like they're going to be punished for positives. And also, people might not actually isolate. And what we're seeing a lot on college campuses are situations where people get that positive test and then don't isolate. CU Boulder has had some of these issues, as have other universities like UIUC. But in terms of the testing actually being able to catch cases before they really explode, yeah, the surveillance systems work. It's really the human behavior that needs to now be incorporated.
Okay. Thank you. And speaking of human behavior, we got this question a lot, and most recently from Christina. She said, how would you persuade people who think testing and mask wearing impinge on their freedoms when I very clearly feel like both serve a greater purpose?
Mask wearing is tricky. And I think mask wearing and testing almost point in different directions, right? They both have a great impact on spread. But critically, when you're wearing a mask, let's say you're asymptomatic and you're wearing a mask, and all you feel is the mask in your face. And, let's be honest, they're like kind of annoying to wear. If we didn't have to wear them, we wouldn't. But you don't really have information with the mask. You don't know that you're infected. It just feels like a burden, and you're not sure whether or not you're really sort of like getting your money's worth. Whereas with testing, it's totally different, right? Because with testing, you're actually getting information. If a test tells you you're positive, that really puts that information in your hands so that you can protect your family and your coworkers and the other people around you. So the mask involves a lot of unknowns and is just purely preventative, whereas the testing, is a much more active process. But critically, with the testing, it needs to be convenient enough so that those people who do feel like there's a barrier there to their participation, it's got to be convenient enough that they're willing to do it. So that's why I really like the saliva-based samples or the anterior nasal samples instead of the deep nasopharyngeal samples. For the sample collection part, it's got to be made easy.
Okay, great. Thank you for that. Next, we have a question from Holly. She said, I'm very invested in rapid testing. Is there any action that I can take as a member of the public to help move this forward? Is there any advocacy work that I can do that you might know of?
Oh, that's such a good question. Yeah, in fact, there's a website that you can go to. It's called rapidtests.org. And at rapidtests.org, you'll see ways of getting involved, reaching out to your representatives, and really trying to move the needle here. It's worth saying that rapid tests exist. It's just a matter of finding ways for them to be approved in ways that the FDA is okay with being out there. So to give a couple examples, here at CU Boulder, out of the lab of Sarah Sawyer, is what's called a LAMP test. And a LAMP test is an isothermal test where you spit into a tube, add some reagents, cap the tube, sterilize the outside, and you boil it. And you do that for about 35 minutes, add it to another temperature bath for about 5 minutes, and that completes the reaction. Then you hold it up to the light and see if it's changed color. If it's either yellow or pink, then you know that it's a positive. So that's about a 45-minute test. That exists. Dave O'Connor's group at University of Wisconsin also has a LAMP test. So this is a common test, results in under an hour. Then there are also antigen tests. Antigen tests like from Quidel has a test, E25 Bio has a test. And these are tests that are more like the lateral flow design. So, the pregnancy test type format, where one line appears if the test is working at all, and then the second line appears if it's a positive. And the turnaround time for those is usually, under 20 minutes. So these tests exist, and you can do some advocacy on rapidtests.org if you're interested in more.
Great, super helpful, rapidtests.org. The next question we have here is from David. He said, what techniques or processes have hospitals implemented to deal with the shortage of tests and the delays in processing?
Well, that's a great question. So hospitals and, as well as campuses and clinics and so on, have gone in a few different directions. So one is something that we're doing here on CU's campus, which is the use of robots to handle a large number of samples. So, here at CU, we have robots at the Broad Institute for MIT and Harvard that's really servicing a huge number of clients around the Massachusetts and surrounding area. They've really got a very streamlined operation there. And all of that just increases the speed at which they can run tests and get results back to people. Then there are these alternative technologies as well, like, again, the LAMP tests. But still, PCR is really the workhorse in the diagnostic labs. We've just found ways to make things more efficient. One way that these tests can be made more efficient doesn't have so much to do with the assay itself, but has to do with how we collect samples. So you may have heard of this protocol that's been developed called Saliva Direct. And it's actually not a testing protocol, PCR or LAMP or antigen. It's really a sample collection protocol. And it showed that you can basically spit into a tube or drool into a tube, depending on your technique. And that sample is stable and reliable to be used. And so that's really nice. That decreases the PPE, right? Because now it's you who's spitting into the tube, not somebody else who's coming into contact with you. So no gloves, somebody doesn't need to wear a mask. They don't need to come at you with the nasopharyngeal swab. And so that really helps as well.
Okay, great. Thank you. Next, we have a question from Wendy. What are the current data estimating the percentage of COVID spread caused by asymptomatic people?
So the COVID spread by asymptomatic people is really tricky because how do you define symptoms? So a lot of people who have mild symptoms end up saying like, oh yeah, now that I've been diagnosed positive, if I think back, I felt kind of crummy a couple of days ago. But if you ask them at the time, do you have symptoms of COVID, and you ask them to fill out a questionnaire, they would say no. And so, a lot of the ability to understand how severe are the symptoms, what is truly asymptomatic, what is pre-symptomatic, what's the cutoff for symptoms, that all gets pretty fuzzy. So unfortunately, there's not a great answer to your question. What we do know is that there's a lot of transmission from people who, at the time that the transmission occurred, they didn't know that they were infected, or they didn't feel sufficiently bad to think that they were infected. Yeah, that's about all we can say there. Depending on which paper you read or which news source you go to, you may get slightly different numbers.
Okay, thank you for that information. Taking a look at the time, we're going to move into our final two questions. The second to last question here comes from John. He asks, how does test specificity factor in? For example, 98% specificity will give 2% false positives.
Right, so the specificity is the probability that, given that you're actually negative, the test actually tells you correctly that you're negative. So 1 minus the specificity is that false positive rate that you mentioned, the rate of people who are actually negative, but who are told that they're positive. So we have to distinguish between the assay's false positive rate and what we call the clinical false positive rate. So let's imagine a scenario, first of all, with PCR. And I'm thinking back to the most recent COVID test I got, which was here on campus. So I walked up to the tent, I swiped my ID card, I spit in a tube, they scanned the barcode on the tube, fine, the test went off. That goes off to PCR, right? And PCR can't really amplify viral RNA if it's not there in the first place. So the specificity of that test is really, really, really good. But from the clinical specificity point of view, we have to think about that whole process. So is there some chance that the folks at that tent were overwhelmed at the time that I got there, and instead of scanning my barcode, they scanned someone else's barcode and swapped the samples? So that kind of thing comes into play. Then with some of the antigen tests, there have been some reports that they aren't as specific at the actual assay level. Okay, so what can we actually do? There are two things that we can do. So one is, first of all, if you get a positive test, you need to isolate right away. But what we can do is a follow-up test, and we can do it in one of two ways. So one way would be to do that follow-up test the next day. And if we can measure the viral loads, so those CT counts, and see that you have a low CT count on both days, that allows us to tell the difference between you were on your way up versus you were on your way down. And if we can identify that you were on your way down in one case versus another, then we have some idea that your positive is yes, a positive, but it's a low positive. Another thing that we can do is give you a follow-up test using a different kind of chemistry. So if we use an antigen test for your first test and we get a positive, to see whether or not that's a false positive, we could run a PCR. And so maybe you end up falsely isolating for 12 hours, but the benefit there is that lots of other people have gotten their true positives. So this idea of a follow-up test in any case, I think is a really good one, to take all those positives and do a secondary test on them.
Okay, great. Absolutely, that makes sense. And so our final question is from Michael. He says, does the CDC, WHO, US government use studies like these that you've shared today to improve or impact their plans?
Yeah, so this is something that we talk about with CDC, with FDA. This work was recently in some of the WHO recommendations. And, the CDC is also thinking broadly about this kind of surveillance testing at different points. So, for instance, in other countries, every time you fly through the airport, you get a COVID test. And so CDC is thinking about the impact of this research in how they think about air travel as well. So just imagine that you go to the airport and you get your rapid COVID test at TSA. And if it comes back positive, then the gate agent calls you up and says, sir or ma'am, we'd like you to not fly today. You have a positive COVID test. Here's your refund and, a mask for your way out. If we were able to basically turn what could be a spreading event into an opportunity for screening, same thing with football games, that would be, I think, a really good thing to do. So CDC is thinking about this. WHO has been using this work. And college campuses have definitely been using this work to try and increase the level of testing on campuses. I hope that we see more and more of that.
Great. Well, thank you so much to everyone for joining us for today's presentation, and a special thank you again to Dan for this great information. At this time, we invite you to provide your feedback on the webinar by answering the following poll question. On a scale from 1 to 10, how likely are you to recommend this webinar to a friend or other CU Boulder alumni? We thank you in advance for submitting your feedback. As a reminder, all webinar attendees will receive an email tomorrow with a link to the recording of this presentation, as well as a survey. To view upcoming webinars, as well as previous recordings, please visit our website at colorado.edu/business/alumni. We hope you will join us for our next webinar, which is next Tuesday, as Professor at the Leeds School of Business, Dr. Phil Fernbach, presents on the knowledge illusion, our current political climate during COVID-19. In the meantime, have a great rest of your day. Thank you for your time, and go Buffs!